Okay, I think we are all set. Yeah, you may just have to bear with me a little bit in terms of the execution because for some reason both the internet and my laptop are a bit slow, but I'm hoping that we're doing good for now. All right, so welcome back. This is the 19th miniature now. And we are looking at a sort of a fun puzzle-like scenario, which is apparently inspired by issues that come up in what is called discrepancy theory, which I honestly don't know anything about at all. So I will just state the puzzle in a self-contained manner. And if you know discrepancy theory, maybe you know why it's mentioned as being inspired by issues that arise there. And the setting is basically one where we've had we've had a rounding problem. And okay, let me just state it from the top. So first, we have a shop that is processing a certain number of orders. Each order is a collection of products. So maybe we have some examples of orders. So here is one. Maybe this is somebody who is planning a wedding or something because their gifts, gowns, shoes, there's some food and wool. Okay, so these products have these prices associated with them. Here is somebody who is maybe planning to learn some sport. This is probably also proposing to somebody on a coffee date or something. So that's the second order. And here's somebody who is probably just planning dinner or something like that. But for some reason also wants a tennis ball or some kind of a ball. Anyway, these are three orders that have come through. There could be many more. Each order is a collection of products. Every product has a fixed price in the inventory. And as you can see, this price has is fractional. And now we are in trouble because of this, because we have a light version of the demonetization situation. So the paisas are now out of circulation. You can only pay in whole number rupees. So the shop owner is tasked with this situation where he has to so where he has to figure out how to do the rounding in such a way that customers don't complain too much in terms of how much their order price has changed. Okay, so hopefully the rounding up and rounding down can reasonably balance out to not create too much trouble. But the reason this is not completely trivial is because you have to determine whether the cost of a single product has to be rounded up or down across the board. So for example, it may in the first order to maybe round up the price of the diamond ring, but in the second order, it may be convenient to round it down, depending on what algorithm you're following. But you can't do that. I mean, you have to fix the price of a product up front and hope that all orders don't change too much in terms of the cost. Okay, so that's the set. So we want to reassure folks that the prices relative to what they were to more. I don't think they would complain if it was a lot less, but that would not be nice from the shop owner's perspective. So we want to make sure that we're still roughly in the same ballpark. Okay. All right. Sorry. So this is probably, can you still hear me okay? Yeah. Okay, in terms of logistics, let me know if I'm still audible. I can try to put my external mic back, but I think that was also somewhat static. Okay.
No, I don't think it's a mic problem. I think it's a network problem.
It's a network problem. Okay. I don't know if, I mean, I've
Yeah,
put my
but I
external
think
mic back in place. I don't know if this is any.
yeah,
It's a
as
net.
Krishna says, it only sometimes breaks briefly, and most of the time we are able to error correct.
Okay. Okay, you're able to error correct. All right. That's okay, that's helpful. Thank you. So let me just in total the order and then round it up or down. That would be nice because then you know that you don't have to change the you'll always be within a 0.5 in some sense. Okay, I mean within 1 rupee, just to keep things simple. So when you total the order first and then round it, then the customer never has to pay more than, let's say, more than a rupee. The owner never loses more than a rupee, or in fact strictly less. So that would be nice. But the reason we cannot quite do that is, it's a nice idea, but the reason we cannot do that is because the products have to be individually, the prices of the products have to be individually relabeled. So the point is that think of this being a supermarket where you just have to redo your whole inventory, right? And now you have to relabel all the products for these new prices. Some orders are already be built in a certain way. That was before the pesos went out of circulation, but now they can't pay that anymore, and so they have to be billed according to these new prices. And we want the new prices to be set up in such a way that nobody has to pay too much more than planned to, and the shop owner doesn't lose too much money either. So the values of the orders should be roughly within a reasonable ballpark of what they were originally. If you only cared one way, I suppose you could just round everything down, and then I think the shop owner would have to incur a large loss potentially. Okay, I have switched my internet network. Is this any better? I still get a message from Zoom saying that the network is unstable, but
Yeah, we can hear you now.
okay. And should I share my screen again?
The screen is visible.
Okay.
It
All right.
says lot of 151.61.
That's right. Okay. All right. Sure. So I think okay, I did think. Yeah, so okay, I missed Manu's point in the chat incidentally. So there are decimals don't make sense on products, and that's indeed the problem statement. So yes, and I'm going to come back to what we what I haven't made a claim yet. Okay, we are going to yeah, I mean, I think we're just going to discover we're going to discover what we will prove with hopefully a couple of examples. So here, if you have lots of orders of a particular item, you can probably see that, well, you could round this up or down. Okay, either way, each order's value will only change by at most 1 rupee, right? So each order by itself is kind of safeguarded. But imagine that you have, well, I mean, let's say you imagine having 100 copies of the same order, all of which have a bunch of different items. But it's all the same order, right? So whatever you do with these, with these items, the cost, okay, you're going to suffer the same cost across all the orders. Actually, I don't know if that's okay. I just intended this to be a baby example to start with. It's not conveying anything particularly deep. Maybe let's just go through a single order. Let's assume that we just have one order, one collection of products, none of which are repeated, right? So every product is ordered exactly once in this example. What would be a good approach to try and so now I don't have to worry about other orders which may also have these items and some other items. I'm just eliminating that by just saying that, okay, this is not a very successful shop. It only has one customer who has placed one order. If that's the very simple setting, then what would be a good way of rounding things up or down? Can we do it in a way that the order value doesn't change very much at all? In particular, can we always keep it within a rupee of the original order value? So any suggestions for how we can go about this rounding? Okay, one idea is that you can round up if it is more than 50 paisa, and if it's less than 50 paisa, we round down. One of those can be greater than or equal to, or less than or equal to, so that it's well defined for everything, so that you're not confused at the 50 paisa mark, basically. With this, though, let's say you have, I don't know, 200 items, which are all 40.99. Okay. You will round up everything to 41, right? And that will add up to a change of 1 paisa for 200 items, right? So you have kind of changed the order value by 2 rupees. And instead of 200 items, if there were like 2,000 items, then you have changed it by even more, right? So Krishna, does it make sense that if you do this natural rounding up, rounding down, then you might change the order value in a manner that is dependent on the number of items in the order and therefore not bounded by a constant? Right. Okay. So Saad is saying we could iterate an order, keep a running loss, and round up or round down depending on the count. And that, if I understand correctly, I think that's exactly the idea that I had on the slides as well. So let's run through it and you can confirm if you agree with what we are going to try and do. So let's just say I arbitrarily start by rounding down because I want to favor the customer. I noticed that Manu has a comment in the chat, and I'll just come back to that in a second, Manu. Okay. So let's say we start by rounding down. So I take off 14 paisa from the first one. I take off 61 paisa from the second one, from the second item. Now, can I round down the third one as well if I don't want to change the order value by more than 1 rupee? No, so I have to round it up. It's a greedy kind of strategy. I have to round it up because if I had rounded down, then I would have incurred a loss of more than 1 rupee. And I want to maintain this as a running invariant that at any point of time, I haven't incurred a loss of or a gain of more than 1 rupee. Okay. So now I start rounding up, and you can check that, well, it's feasible to round up again, and it's feasible to round up again. But at this point, what has happened is that you have increased the order value to 92 paisa compared to what it was before, if you do the roundings that we have done so far. So we cannot therefore round up again because that would increase it by 9 paisa, crossing the threshold of 1 rupee ka change. So now I'm going to round down, okay? And that's going to bring it all the way back to whatever, a change of only 1 paisa, right? So is this algorithm or this method for rounding kind of clear? Awesome. Okay. So in general, your current order value is, it's somewhere, right? Or the current amount of, okay, let's say the net loss or gain that you have, the net change that you have is somewhere. And now you're faced with the next option where maybe rounding up will take you beyond the 1 rupee threshold. But if that happens, then rounding down is always safe because the round up plus round down will add up to 1 unit, right? On the other hand, it's possible that rounding down takes you, below the 1 rupee threshold, in which case rounding up would be a safe thing to do, right? So basically, my point is that one of these options will always be viable. Is that fine? Okay, great. So we kind of keep doing this. And Saad, was this sort of your idea as well? Just going over the items one after the other and rounding up and down as appropriate? All right, perfect. So this is a fairly natural thing to do, and it works great for one order. Okay, so with that sort of a warm-up, let's come to the claim that we want to make. So, well, no. So the thing is, Manu, I focused on just one order. So it's that this price is going to be fixed for all subsequent customers. So now it's really not clear that this works when you have multiple orders. If you have multiple orders and everybody has ordered different items, there are no overlaps, then this will continue to work. But if somebody else also has, let's say, I don't know, somebody else has the ring and the gown and they have some other things, then maybe the way that we have rounded up and down here may not be well suited or compatible with, a strategy that we apply on their order. So we end up with these conflicts. So it does, I think this is a very good point, that it will get more challenging as you add more orders and, there are the overlap in funny ways across products. So, okay, let me now come to the main claim that is being made.
So different orders, different orderings will give you different values, right?
That is also true, right? So with different orders,
if you want to minimize the overall thing, is that the idea?
Right, you want to minimize in some sense the overall sort of damage.
Globally, you want to minimize this across all permutations, or?
Okay, no, that's I don't think so, although I think that's a perfectly valid alternate question as well. But maybe just to address what you asked, let me bring up what we will actually end up showing, which is that the total, we will come up with a rounding strategy so that each order has a price change of at most T rupees under certain assumptions. So products are not repeated in orders. That's, I think Manu was talking about repeating items, and that is something that we kind of eliminate because hopefully that's intuitive. Because if you want to prove something like this, okay, sorry, that's my machine acting up again. So you want to, okay, let me just wait for the correct slide to come up, and hopefully you're seeing the statement now. So, so Manu, just to address your question, if you allowed for multiple copies of the same item, then let's say somebody has for some reason ordered 100 diamond rings, right? Then no matter what you decide to do, round up or round down, the price of that order is going to change in a manner that depends on the number of copies of that item, right? But what we want to do is show that as long as the number of, okay, maybe this is subsumed. Okay, so what we are saying is if we have a bound on how frequently a product was ordered, then we can have a rounding strategy which changes the order amount by no more than that frequency bound. Okay, so we know that every product has been ordered at most T times across the board. You look across all the orders. So maybe let me go back to the first example that we had. Okay, somehow that slide's not showing up. Yeah, so I think this was the example. So this was the example we started with. And if you look at these items, they have been all ordered twice, and the other items have been ordered uniquely. So basically what we are saying is in this setting, in spite of the orders being intermingled in messy ways, I can still come up with a global rounding strategy which changes the price of each order by no more than 2 rupees, right? And I did not put in enough effort into rigging this example, but presumably you can rig an example where there is no rounding strategy, which will keep the price difference to strictly less than 2 rupees. But that's actually worth thinking about. I haven't thought about whether this result is tight in that sense. However, what we are basically saying is if the frequency of products being ordered across the board is bounded by some T and products don't repeat in an order, then then we can come up with a nice rounding strategy which changes the price of each order by at most T rupees. And I think, okay, when Manu is saying if you take a large number of orders and try to do this one by one, this looks like a small training data set and, things are unpredictable and so on. That's a good point. So I think the setting of this puzzle, I have to admit, it's not a very real world setting. We are assuming that all the order information is in front of us, it's in our hands, and we are not trying to either predict any patterns or account for information that we don't have. So those would be really interesting extensions to look at. But for now, you just assume that you have all the information on hand. So it's a very in that sense, it's a very constrained setting. Okay. And it's further constrained by these assumptions. But I want to argue that these assumptions are kind of reasonable because, if you have a lot of copies of a given product or it's being ordered very, very frequently, then there's nothing much that you can do, right? So like I said, if somebody orders 100 diamond rings, you will no matter what you do, your order value is going to go up or down as a function of the number of copies that have been ordered. So there's no working around that. That's something you cannot help. So to keep things simple, we just assume that you don't have products being ordered in multiplicity, although I think this can be extended easily to account for multiplicities, but it'll affect this. It'll affect the claim. The claim would also have to be updated to account for multiplicities, right? Right. So Joel, I think, once you go into the realm of the unknown, I think we will need a lot of other moving parts to, even specify the problem completely. But for now, just think of this as a silly combinatorial puzzle, if you will, right? So you have a large number of orders potentially. And the reason I'm saying a large number of orders is to make this result sound a bit impressive. So notice that the change in the order value is independent of the number of orders. It's independent of the number of products in each order, and it's independent of the number of products in your inventory. It's only dependent on the frequency with which any given product has been ordered, right? So, right, when I say order, you're confused with whether the set is ordered. I think except for when we went over the algorithm and we processed the products one by one, we did it in some order. Actually, that order was not important. It could have been any arbitrary order. But for now, whenever I say order, you can think of it as a collection of products. I did not realize that that term would lead to, would be overloaded in this fashion, but we are almost never talking about a permutation or an ordering. So I think you can think of the word order as a set. In fact, we will switch to calling it a set very soon now as we get into the proof. So yeah, I think, let me just quickly ask if the claim that we are making makes sense. Yeah, we want to show that if the products have been ordered, if every product has been ordered or asked for by at most T customers, and every order consists only of distinct products, then there's a rounding strategy that changes the total price of each order by no more than T rupees. Does that make sense? Okay, wonderful. And I think I should not have spoken too soon about this being a short miniature that we will finish quickly. So you might have to bear with me for another 5 or 10 minutes as we try to figure out why this works. We have some of the intuition already, but let me try to build a little bit more. This is a reformulation with a little bit of additional notation. I don't think this is spectacularly important, but what all that's useful to remember is that we have a global pool of items, which we are denoting as 1 to n, and every order can be thought of as a subset of these items. Okay, so I'm going to use SI to denote a subset of n, and that's all the products that are sitting in the ith order. And we are assuming that no j occurs in more than T sets. That's the frequency bound. And the reason I can use set notation is because products are not repeated. So these are not multi-sets, these are actual sets. Okay, so the products are labeled from 1 to n. Each order is a subset of 1 to n, and each index appears in at most T subsets. That's the setting. Okay. All right, so now I've switched to having on top the claim that we want to prove, and let's say that an order is nice if it has fewer than T products. Why are such orders nice? Given what we are trying to prove, why would I call this order nice? Exactly. We can round this any way we want. No matter how the products get rounded, no matter what strategy we apply, with small orders, we are going to have no trouble, because even if every product was rounded in a very suboptimal way, the value cannot change by more than T rupees. So in fact, instead of fewer than, I could have even said at most and gotten away with it. So if you have at most T products, these are orders I don't have to worry about at all. Okay. So the troublesome orders, is this clear? Yeah. Okay. Awesome. So on the other hand, the orders that will need to be accounted for are the large ones. So you have more than T products. So let's think about the relationship between the number of products and the number of large orders. Okay, so for this, it's useful for me to draw small graphs. So let's say on the left, we have products, and on the right, we have orders. And let me draw a line between a product and an order if that product belongs to that order. Okay, so these are elements of 1 to n on the left, and these are sets on the right. Okay. How many lines are coming out of each element? If I look at the left, how many lines are coming out? Remember, our assumption is that at most T pieces of each product have been ordered, right? So on the right, we have all the large orders, but still we know that every product has been ordered at most T times. So how many lines are coming out of each of these stars? T lines or at most T lines? Exactly. So we have at most T lines coming out of the stars. On the other hand, these are all large orders on the right hand side. So how many lines are coming out of the large orders? By definition, at least T, exactly. So yeah, okay. So I said the large orders are more than T products. So let's say that these are more than T lines. Okay. So if we just counted the lines, how many lines there are, looking at it from the left, we see that the number of lines is at most T times the number of products. But on the other hand, looking at it from the right, I see that the number of lines is strictly more than T times the number of large orders, right? So does that make sense? This is called a double counting argument because you're looking at the same set of objects, in this case, the number of lines, and I'm counting it two ways, right? From the left, I know that the number of lines cannot be more than T times the number of products. And on the right, I know that the number of lines has to be greater than T times the number of large orders. Does that make sense? Okay. Now from here, can you tell me what's the relationship between the number of products and the number of large orders? Which one is bigger? Products. Perfect. So we just drop this T from both sides and drop the number of edges to see that the number of products is more than the number of large orders. So just keep this at the back of our mind because this is going to be useful later. And now we sort of come to what you might think of as the proof of the claim. So we are going to introduce n variables. This is where our linear algebra comes in. So we introduce n variables, and these variables basically represent the final price of the ith product. I forgot to say this, but we can basically assume that all product prices are between 0 and 1 because the whole numbers don't really matter. So just as a matter of convenient convention, assume that all these prices are between 0 and 1, and we're trying to figure out, should we round it down to 0, round it up to 1, okay? So these xi's will be representative of the values, that the rounded values, but initially we initialize them to the original prices, okay? But we will let them evolve and finally reach a 0-1 state. And hopefully we'll be able to prove that the way we have done it, the order values are not tampered with by too much, okay? So we have n variables. All of them are, the ith variable is initialized to the cost of the ith product. And now we are going to try and, so this was the goal, as we just said. And our terminology is going to be that if the value of xi is strictly between 0 and 1, then I'm going to call it a floating variable, both because it has not reached its final state, and also because you can think of it as a floating point value, strictly floating point value. And it's final if its value is either 0 or 1, because then I'm like, I've determined what I'm going to do with the ith product. So is the terminology so far clear, or is anything sounding confusing? You may not see where the proof is going just yet, but is the are the definitions kind of okay? We've just introduced n variables whose values are initialized to the costs of the products, right? And we call them floating or final, depending on whether the values are rounded or not, okay? All right, awesome, thank you. So now what we are going to do is work with dangerous orders, okay? So in general, for me, an order is dangerous if it's large, if it has more than T items. But now more generally, I'll call a set dangerous if I look at the products and I look at the corresponding variables. And if there are more than T floating variables, T variables whose values I have not yet determined, then I will call such an order dangerous. So to begin with, initially, all my large orders are dangerous because all variables are floating. Let me just assume that all product costs initially were strictly between 0 and 1, because we can forget about the ones that weren't, doesn't affect anything. right? So initially, all the large sets are dangerous. As we start fixing more and more values, some of them will start looking less scary, because as we go along, we are going to maintain this invariant. The invariant is that the cost of all the floating variables, the value of all the floating variables adds up to the original cost of the corresponding items. Okay, so for all the dangerous sets, I'm going to maintain this. I'm going to maintain this equality. Okay, and now notice that this sum is actually over all the products in the set Si. It's not only over the floating products. It's overall products. Okay, so I'm only going to focus on dangerous sets. Okay, the ones where when is a set dangerous, I go into the set, and for each product, I ask, is the variable that's representing you currently floating or fixed? Final. Is it floating or final? And some people will say, well, I have been finalized. Some people will say I'm still floating. So in an order, if the number of products who say I'm still floating is more than T, then that order is dangerous. Okay, so is the definition of a dangerous order or a dangerous set clear? Okay, awesome. So now we are going to interpret this collection of equations that we have written here. We wrote down these equations for all the dangerous sets. We are going to interpret these equations as a system of linear equations where if a xi is finalized, we just substitute its values. If a xi is 0, we forget about it. If it is 1, we add a 1. So those are going to be constants. If they're floating, we write them down as variables. And on the right-hand side, we have the total value of the order, right? So this is a system of linear equations. What can we say about the relationship between the number of unknowns and the number of constraints? Notice that the constraints correspond to dangerous sets, and the unknowns correspond to products whose values we have not yet determined. Which one do you think is bigger? The number of unknowns or the number of constraints? Or do you think they can potentially be the same? Okay, Jayati is saying I should repeat the maintain condition. So the maintain condition is saying that the sum of the variables that correspond to the products in a set Si, the sum of those variables should be equal to the sum of the total original cost of that order, right? So the set
So
Si...
I think that I belonging to Si is a problem. I think that may be the issue.
Oh, I see. Okay. I think I kind of was lazy about just borrowing that. So maybe, I don't know if... I can just change this. So the SIs are the dangerous sets. I'm looping through. Okay, is that better? Okay, sorry, I think I just updated the index variables. I don't know if that looks more reasonable now. Okay, all right. So so it appears that Jayati has confirmed that the maintain condition is okay. And just to respond to Vinay's comment, I don't know if I lost my internet again, but the index is indeed a bit confusing. SIs are the dangerous sets, and we're looping over everything in SI on both sides. So the that represent the products of that order. Relationship between the number of unknowns and the number of constraints is a hint. Let's think about what happens at the very beginning, right? So all the dangerous sets are simply the large sets, and all the unknowns are simply all the products, right? All the products that belonged to large sets. So do you remember what we said about the relationship between products and large sets? And can you apply that here? Yes, exactly. So I think Joel has said exactly what I wanted to say. In the beginning, we know that the number of products is more than the number of large sets. And so products correspond to sets, which is large sets or large orders, right? And we have already reasoned that basically the intuition is that products don't appear too frequently. So if you have a lot of large sets or dangerous sets, then you do need a lot of products to be able to account for them, right? So that's what's happening here too. So the number of unknowns, well, every unknown, if you pick a random xj, right, it's only going to appear in at most t constraints, because every product was ordered at most t times. Sets are large, they have more than t floating variables. So to be able to generate all these dangerous sets, right? To be able to generate these constraints, you need to have enough unknowns to be able to account for all of them. And if you want a more precise argument, you can do the same work to enable you to conclude that the number of unknowns is greater than the number of constraints. Okay. What can we say about a linear system where the number of unknowns is more than the number of constraints? So if fewer constraints, more unknowns, that's I guess more freedom. So what can we say? Right. So this is an underspecified system or an underdetermined system or underwhelmed system, whatever terms how many solutions is this going to have? Right. So an underspecified system is going to have infinitely many solutions unless the system itself has some sort of a contradiction, right? So for example, if I say that x plus y plus z equals 0 and x plus y plus z equals 1, those are just mutually incompatible constraints. So if you have something like that, right, then it has no solution. But on the other hand, if you have at least one solution, then you have infinitely many solutions, right? Now, this system here is not it's not a contradictory system. And the reason is that we know of at least one solution, which is to simply set all the xi's to the corresponding ci's, right? If you took all the xi's and simply set them to ci's, then you would trivially satisfy all of the constraints, right? So do we agree that this system of equations has infinitely many solutions? Awesome. Okay, so now that means that, okay, so this is an undetermined system with at least one solution. So, all right, I have a warning from Zoom about the internet. So, all right, seems to be stable again. So, okay, we know that it's an undetermined system with at least one solution, which means that we have a non-trivial solution space. The solution space has dimension at least one. It may be more. That depends on how many more unknowns you have relative to the number of constraints. But you mentioned at least. Notice that CI is basically one out of this d-dimensional cube, where d is the number of floating variables. Those are the variables in our system. Those are the number of unknowns variables that what we are going to say that, okay, you have a cube and this which in the solutions of the cube, okay, which means that you have found another solution that satisfies all the constraints, but this solution is sitting on the boundary of this cube. What does it mean that the solution is sitting on the boundary of this cube? Nice for me. Can I use such a solution to get to finalize some floating variable?
The last part, I don't think any of us got. I think your voice trailed off for about a minute or something.
Okay. Oh, I see. And so I will just repeat myself. So, okay. Yeah. Sorry, what was the last thing that was kind of okay?
The infinite number of solutions, and you said, yeah. And I think these.
So there are an infinite number of solutions.
Yeah. Yeah, and then I think these.
Yeah, we sort of agree that there are an infinite number of solutions. Right. Okay. So I want to migrate from the solution that I currently have to a solution that has hopefully one less floating variable. Okay. I want to somehow use the solution space to move to a nicer solution, which fixes some of my variables. Okay. Now I know that at least one solution that I have is set all the xi's to ci's. So it's sitting inside this d-dimensional cube, right? Where d is the number of unknowns in this system. Okay, so it's sitting inside this cube. But I know that the solution space is dimension at least one, which means that I can at least find a line that contains my current solution. And I can walk along this line until I hit the cube, until I hit the boundary of the cube. But what does it mean to hit the boundary of a d-dimensional cube? What is the solution? So if I look at the intersection of the boundary of this cube along with the solution space, what do those points look like? Are they special in some way, especially from the point of view of being able to fix some of my floating variables? So I stay in my solution space. Yeah, they're no longer floating. Exactly. So if I move, okay, if I can get a corner point, I think that would be great, because then I can probably fix everything. But I don't know if this line is going to hit the cube at a corner point, but it's going to hit it. I mean, I'm going to have to cross the cube at some point. And if I cross the cube, then I know that at least one of the coordinates would be a 0, 1, as Jagdish is saying. So I migrate to that solution, right? And I fix one of my variables, okay? So basically that's a nicer solution for me, because now I have one less floating variable to worry about. Maybe many variables get fixed if I'm lucky, but at least one definitely gets fixed, okay? And now I update the status of all these sets. Some sets that were previously dangerous, some may be no longer dangerous, and I rewrite my system of equations. It still has a solution, because the solution we are working with right now would still work, except some of my variables have now become constants, right? And so I just basically repeat this process until is the process clear? It's the process of arriving, fixing all the variables. Is that okay? Okay, an example would help. All right. I unfortunately didn't do an explicit example, but the idea would be, okay, so maybe I can actually pull up an example offline and share it, like a concrete example that we could fully work through. But the idea is that in principle, you have this system of equations. You have an initial, let's just think about what happens at the very first step, right? All the xi's are simply set to ci's. And now you look at the system of equations just for the large sets. You realize that you have, a solution space that's large, right? And there's one solution that sits inside this hypercube, or this 0, 1 to the f, right? That's your current solution. You don't like it because it consists of all of these floating point numbers, right? So the idea is that you take help from your solution space, but to navigate to another solution which sits on the boundary of the cube. And that's a better solution from your point of view, because that solution is going to have at least one of these variables set to 0, 1. So now I migrate to that solution. The variables that are 0, 1 in that solution are now no longer floating. They become fixed. Okay. And now I rewrite my equations, getting rid of some of these variables. And now maybe some sets that were dangerous before are potentially no longer dangerous now, right? And now I repeat this process again, and I know I'm making progress because at every step, I'm fixing up at least one floating variable to a fixed variable. And I stop when all of them have been fixed. My claim is that this is a rounding strategy that does not change the value of any order by more than t. Okay. And let me just briefly explain why that's true, because that will motivate why we wrote these constraints in the first place. So think about your favorite order. Okay, if that order to begin with was a small order, then you don't have to worry about it. So let's say that it was a large order. So to begin with, it was dangerous. Okay. And as we went through this process, at some point it transitioned from being dangerous to not being dangerous, right? And up to that point, up to when it was dangerous, we actually maintained this invariant, which meant that with all the variables that we had fixed up to that point, we actually completely maintained the order value. We did not change it at all, right? And once it stopped being dangerous, we don't care because we are only changing the values of at most t items in the order. Does that make sense? Oh, how is the invariant being maintained? Well, that's a process. Okay, so that's the process of just moving across your solution space. So, okay, so to begin with, you had one set of equations, and there was one trivial solution, which was that just take every xi and set it to ci. This is not a very useful solution because everything is floating, right? Now, assume that I have a black box way of giving you another solution that satisfies all of these equations, but fixes at least one floating variable, right? That black box method is actually just starting with the first solution and then, trying to use the solution plane to go and hit the boundary of the cube. But if that part of it is not clear, just take it as a black box for now. So suppose I have a mechanism which I guarantee exists and works as advertised, okay? A mechanism that can transform a starting solution, a solution that respects this entire system of equations, and gives you another one where at least some of the variables get fixed, right? So I migrate to that solution, okay? But now I rewrite my equations, and I know that the equations are all, still satisfiable because I have this solution that I got from this black box procedure. So it's still a satisfiable system of equations, but now some of the variables have disappeared. Some of the xi's, which actually became 0, 1s, are now being replaced by constants. So in some orders, some products had their values actually rounded up or down, so they got fixed. And potentially, if an order had, let's say, t plus 1 products, and now one of the products got fixed, then it now only has t products. So now this order is no longer dangerous. So it will leave my system of equations. I no longer write down a constraint for it because I don't have to worry about it anymore, right? So now basically I have a new system of equations after all these variables have been overwritten, the ones that got fixed. And this is I can repeat the exact same story now, saying that, look, this is a satisfiable system of equations. It still has a collection of constraints that correspond to dangerous sets. Every product still appears in at most T of them. Therefore, the number of unknowns is still bigger than the number of constraints. Therefore, it's still an undetermined system with at least one solution. And therefore, I can again migrate my solution to a point that fixes some more floating variables. And I keep doing this iteratively.
Yeah, I think I know where the problem is. Let me try and see if we can.
Sure.
I think probably the main point is that when you initially start, right, at that point, it is true that you can take Xi's to be Ci's and the equations are satisfied. But after that, Xi is equal Ci is not what gives you a solution. Okay. After that, it fails. After that, I don't know. Can I draw something?
Oh, yeah.
The annotation.
Okay, sorry, it should be enabled now. Sorry.
Yeah. No, so suppose you had a square, right? Something of this sort, and you had an interior point. This is your x1 equals c1, x2 equals c2. You go somewhere and you hit a corner, you hit a face of the cube, and so this point is fine. But now now you have to move either up or down or something of that sort, right? But this point is no longer the xi equals ci point. Now we have moved to a new interior point on that line. So only initially is it true that xi equals ci. After that, this is your new interior point.
Correct.
Am I making sense?
Yes, that's true. Now, if we pick up this point on the boundary, do we have, because it's connecting these two corner points, do we have that at least one of these points, one of these coordinates is a 0 or a 1?
No. The fact that it is on this face automatically means that one of the coordinates is 0 or 1.
Exactly. Right? But it's still a solution to the whole system because it's on this line as well, right?
Yeah. No. I think when you said, right, it looked like I am at some intermediate point. The invariants are already established. At the intermediate point, it looked like you said xi equals ci is a solution to this. I know it's underdetermined system, and xi equals ci is a solution. I am claiming it's only true at the beginning of the iteration.
That's a good point. Okay. So I'm just going to maybe fix that by saying you're right. So xi equals ci is at an intermediate stage. The solution is the solution that we got from the previous round. And we have to trust that.
Yeah. So you have to,
Yeah, that's right. So the red arrow is pointing at a line which justifies the fact that we are still working with a valid solution because that's on the line that has been drawn in the solution space. And the pink arrow points to the line that assures us that's the reason for being assured that the solution fixes at least one of the floating variables. So we have basically moved to a superior solution. It's still a solution that satisfies all the equations, but it has at least one more fixed variable. So now I've gotten rid of something, but I still satisfy all the equations. So I'm overwriting some of these xi's with zeros or ones based on what the solution tells us. And that's the solution that gets pushed forward to the next round. So Krishna, I don't have the black box. Like I think when I opened up the black box a bit, and hopefully that now makes sense.
Yeah. So xi equals ci is the solution when you start the process.
Correct.
And throughout, as you keep going to a lower dimensional phase, okay. For example, if you had a 3-dimensional cube, maybe this would have hit actually some point here, and you would have had a 2-dimensional phase here. Okay. A 2-dimensional cube and so on and so forth. And you maintain that solution throughout. That's it.
That's right. I think the reason maybe even in the miniature, the phrase is still that xi equals ci works is because even in your interim iterations now, your space of variables has reduced. And if you only worked with, and the other variables have now gotten replaced with these sort of constraints, right? So
but suppose if xi has got set to 0 to 1, right? One of the xi.
Yeah, right? So that xi is no longer.
So this value has changed, no? Yeah.
Sorry?
So that xi, so it no longer exists. So either you make sure that your SIs are redefined. Or if you want to
Right.
keep your old SIs and modify, then this right-hand side has to change, right? Because now there's a +1 here somewhere, right? Because your, x10, you made it as a +1. And now we have
Correct.
to rewrite this equation, right? So,
Right. So the equations are definitely getting rewritten at every step. And some equations are completely disappearing because they don't have enough floating variables. So
yeah,
if
so
you
once your
keep,
equation gets rewritten, the notion of xi being equal to ci doesn't make sense, because the ci's have no longer any meaning anymore. This has vanished. Okay. Now this has
well,
become
I mean,
-1 here. Yeah. And this has
well,
become a smaller equation. Yeah.
right. Has it become a -1 though, in the sense that the CIs are still, I mean, the right-hand side is still fixed, is it not?
No, it is not. No, so I mean, you can think of it, no? Let's say I had x1 plus x2 equals c1. x1 plus x2 plus x3 is c1 plus c2 plus c3.
Right.
Right. And at some stage, I decided that x3 is going to be +1. Right.
Right. Okay. And okay,
So now the
fine.
equation is going to become x1 plus x2 is c1 plus c2 plus c3 -1. Right.
Correct.
So now you can't claim that x1 equals c1 and x2 equals c2 is the solution. The solution that you can now claim is this point here, whatever this point is. Okay. That is the solution.
No, this is true. Okay, I may have to, yes, as I may have to just sleep over it to be sure. But my impression was that once the equation becomes sufficiently small in terms of the number of variables that are there on the left-hand side, those equations just are gotten
Will
rid
vanish.
of the system,
No,
right?
it will vanish in the sense that you don't care about it anymore.
We
But
don't care
nothing
about
prevents
it.
you from, nothing prevents you from
Right.
having those equations. Yeah.
Well, we don't solve for them though. That's kind of,
Yeah, you don't care about it, but it doesn't. I mean, because the bound gets satisfied anyway.
the bound gets satisfied. So basically, at the
It's
end,
fine.
we have a junkyard of these constraints,
Yeah.
which have only t variables on the left, and now we don't care about satisfying.
Yeah. But I mean, if you want, I mean, we can do x1 to x10, right? And let's assume that t is 3 or something.
Okay.
Yeah. So you can have
So,
x1 to x10 equals c1 to c10. x10 becomes +1.
right.
Okay. Yeah.
So
Or
now
even if x10 becomes 0, right?
correct. So then that
you
would
still
be
have a problem. Yeah.
okay, a problem in the sense that, okay, so if my claim is that if x10 becomes 0, then I have x1 through x9 is the sum of all the CIs. And if it becomes 1, it is like you said, it's x1 through x9, the sum is equal to the sum of the CIs -1.
Yeah, but at this stage, this is a step 1, right? I have iterated once, and xi equals ci is no longer a solution of this equation.
Okay.
Right? Because I have dropped x10. No? x10 became 0. So x1 to x9 is not going to add up. If I substitute, I'll get c1 to c9.
Sure. So I think these exercises are solved by what.
Yeah, because I mean, I was here, and while one of the variables became integer, the other variables changed because you are going on a slope, right? Yeah.
Absolutely. Yeah, sorry. I think I now see what you mean with xi equals ci not being the justification going forward. I think certainly you hang on to the solution that you got from the previous iteration to justify that you still have at least one solution, even for the new system of equations. And then you extend it from there. But in the meantime, the character of your system has also changed a bit. And you do have to, I think it is also important that you drop the equations that have too few variables on the left, because it's only when you drop them that you can still justify that the number of unknowns is more than the number of constraints, which you need to say that the system is underdetermined. So that cleanup is important, and hanging on to the solution that you got from the previous iteration to justify that there's still at least one solution, both of these are key. And you're right that I think the notion of xi equals ci is only true to begin with. And I should have been clearer that the justification for at least one solution in the ith iteration is that you have the solution from the previous iteration. It was still a member of the solution space, and it continues to satisfy all the equations that we have now. So, indeed, that I completely agree. Yes. So, sorry for some time there, I don't think I understood the issue, but now I do. Okay. All right. So, Okay,
Is
so
it
I
clear to
think
the rest of them? The question.
I hope so. So can someone let me know if this looks good? So Krishna, I think we were good as long as we said that we have some way of moving to a good solution. And I said it was a black box. And now hopefully it's clear that the way the black box operates is by taking the solution we know we have, which to begin with is xi equals ci. In the ith iteration, it's the solution that we had from the previous iteration. We take that and we know that it's sitting inside this cube. And we know that we have a solution plane to move along, or a solution line at least. So we move along that line till we hit the box somewhere. And since we're going to cross the box at some phase, we know that that's going to trigger some of the coordinates to 0. So 0 or 1, of course. Yeah, so 0 or 1. So hopefully that's not much of an assumption anymore. And thanks to Jayati for confirming, and a couple of others maybe let us know if we are good. I agree that maybe I should have just worked through a full example. Yeah, okay, all right. So fair enough. I think it's hopefully makes sense in an overall sort of way. And I don't know if this result is tight in the sense that are there examples that we can come up with that satisfy the premises of this statement, where no matter how you round things up or down, you cannot do better than guaranteeing T rupees ka bound. Like you cannot say, oh, it'll not change. So yeah, I mean, I want to say that this claim is tight in some sense, but that would require a backup example. And it's not clear that I have one. Yeah, certainly I don't have one right now, but it's worth thinking about. Okay. All right. So fine. A high level concept is just to say that realizing that if small orders are easy to deal with, and somehow you want to weed out or fix things in large orders in a way that's meaningful, in a way that doesn't touch the total order value at all. And the way you do that is by this little counting argument that gives you this underdetermined system, and this iterative process that makes sure that these systems are never inconsistent. So those are kind of some of the keywords of the ideas that went into this proof. And I think between my logistics hurdles and not properly anticipating maybe how much this would take, I think I've overshooted by quite a bit more than I ever have before, I guess. So sorry if there was like lack of clarity logistically and otherwise, but it's a really cute I mean, somehow I did feel that this one had a set of ideas that were cute and accessible. It only uses linear equations and like a cute counting idea to make that idea work. And the process is algorithmic and iterative. So maybe that's why I thought it was. I mean, maybe that's why I kind of ended up really liking it, and I hope you like it too. We will pick up this conversation tomorrow because I think I've already kept you folks quite late. So thanks very much for joining and staying. For anybody who wants to stay back, you're very welcome. I'll be around, but this is where I'm going to end the official stream.